Thank you. Good afternoon, everybody. Thank you very much to the organizers for having me here. I'm very happy to be here. So I'm a PhD student at NTU Singapore, and the title of my presentation today is Decoding Neurophysiological Mechanisms and Complex Brain Networks Using EEG and Machine Learning in Brain-Computer Interfaces. So far, we have already seen some very interesting talks on brain networks, but they were on fMRI or on structural and functional connectivity using neuroimaging modalities. Here, I would like to give a perspective from an electrophysiological recording. Right. So I would like to set the stage for my presentation by highlighting that there are mainly three different types of communities which study the brain. Those which compose of neuroscientists, clinicians, and engineers, each of them studying the brain from a different perspective, right? Because the brain is so incredibly complex. So one of the key motivations for me as a researcher is to try and bridge the gap between these three different communities. And I guess the best way to do that is with the help of data-driven engineering. For example, we have brain-computer interfaces which are building more translational devices, for example, smart prosthesis and so on. But we can also use them to try and uncover some of the fundamental science behind the different brain mechanisms. And together, this combination of science and technology can be used to help patients of different diseases such as stroke, autism, and so on. So today I'll be addressing some research questions which handle data-driven techniques to decode motor activity in particular. So for example, what is the neurophysiology of different motor activity? How can we use AI and incorporate these differences in different brain networks and brain interactions to decode single trial hand movements? And lastly, how can we use this as a paradigm to validate our initial hypothesis about how we think about how the brain works? So Tiffany has already given a very good introduction about what are brain-machine interfaces. So I'll just very quickly go through this. Firstly, you have brain signals which are acquired, and then we use some algorithm to extract the relevant features. Typically, we use some machine learning-based method to translate these features into commands which can be then given to a number of different applications. Right, so now we would like to model different types of neurophysiological mechanisms, and my friends who are already very well versed with brain networks already are very familiar with these concepts of functional segregation and integration. So basically, this basically looks at the brain in two different perspectives. The first one is functional segregation. And that talks about the brain as comprised of specialized areas, and each area is being responsible for a particular task. So visual cortex responsible for vision, motor cortex responsible for motor activity, and so on. And at the other end of the spectrum, you have functional integration. And this talks about the brain as working with the help of integration of information from different parts which are in it. Well, what happens in reality? There is a balance between these two concepts, right? Because that is how the brain achieves the maximum efficiency. You cannot have different brain regions working in isolation of each other. At the same time, you cannot have every neuron as being connected to every other neuron, because that would be so inefficient in terms of the wiring costs and the resources involved. So the brain actually is able to achieve a balance between these two concepts. And this is the type of interaction that we will be modeling, right? So the talks earlier have already spoken about what are the different ways in which you can model different interactions between different brain regions. So for the purpose of my talk, I'm talking about functional connectivity, which, as has been mentioned earlier, is basically means that the edges between any two given any two given regions is estimated from the statistical dependence or a statistical measure between these two, the data coming from these two regions. And typically, once you have estimated the functional connectivity, you can visualize it with the help of a graph or with the help of a brain map as shown over here. Right. So how does all this fit into decoding hand movements? Right. So on the right over here, you see that there is a subject who is wearing an EEG cap, and he is holding an MIT Manus robot. Many of you might already be familiar with this MIT Manus robot, which basically records the movement parameters in real time. The parameters include things like force, direction, trajectory, and those things. So that is used to establish the ground truth, right? And EEG is being recorded simultaneously. So in this particular case, the patient, the subject, moves the MIT Manus robot in one of 4 directions: north, east, south, and west, right? So up till now, the most popular way of decoding motor activity from EEG was with the help of common spatial patterns, right? So this is, the original paper was published way earlier in the year 2000, so they've been around for about 2 decades, and many, many variants of this algorithm have been proposed in literature. And the reason why they're so popular is because when you look at what do they do? They basically find the most discriminative set of spatial patterns of activation. So for example, when a variant of this algorithm called wavelet common spatial pattern is used on this particular type of task, what was found, you can see over here is that in different directions, you can find a very different pattern of activation. Now this, if you would give to a typical machine learning pipeline, you would have a decently working system in terms of decoding which are the 4 directions. So what's the problem? The problem is that moving on to more complex hand movements, right? Neuroscience, as well as various studies using MRI, have shown that the brain regions which are involved in the control of motor activity, which become more complex, and when you're dealing with single hand movements, like for example, finger movements and wrist movements, these different brain regions begin to show a large amount of overlap, right? Now, if you have largely overlapping brain regions, which are responsible for different types of hand movements, you can naturally expect, at least theoretically, that a method which is based on common spatial patterns will hit a threshold, beyond which you cannot expect a further increase in accuracy. This is, of course, it is yet to be tested out, but it is an intuition that we can see from what we know so far. Right. So if this is what we expect, how can we model the brain interactions in a better way, right? And that is with the help of brain connectivity. Okay. So the kind of interactions that we are modeling over here is finding some way to find a stable estimate of brain connectivity on a single trial basis, which can then be used to classify different types of movements. And that the hypothesis there is that different parts of the brain will actually coordinate differently in order to carry out different hand movements, right? And if we are able to estimate and identify these differences in interactions, can be in space domain, time domain, frequency domain, if we're able to get that and identify the different interactions in form of different graphs, then maybe we will be able to identify different complex hand movements. But moving on to this, we know that there is a problem wherein it's not very intuitive to associate an entire brain graph to different types of hand movements, especially when movements become more and more complex, right? And moreover, now we're not looking at different regions and at different activation patterns of these different regions. We're looking at the interplay between them. So that means the computational complexity is going to grow substantially, right? So how do we tackle this? Well, step 1. And this is the first part of my research, where I use a measure called wavelet phase locking value, which is basically a modified version of the original phase locking value that is there in literature. So this is used as a measure of statistical dependency between the data from different EEG channels. So for over here, you see we use a total of 35 EEG channels. And then we estimate the brain, the connectivity between all possible pairs of the channels. Now, this is purely data-driven, right? There's no assumption on what are the different nodes, in this case, what are the different EEG channels that are involved, and so on, right? And what we see over here is, after we perform a permutation-based statistical testing and we only retain the significant links, what we find is that for the 4 different directions, you have different types of interactions that are present, right? But this is done on a trial averaged basis, when you have enough data to average your trials and then reach that stability, right? How are you able, or how can we do this on a single trial basis? Okay, so Many of you will be able to quickly identify that this is a typical machine learning paradigm. There's nothing very, very new about it. So I would like to instead highlight 2 steps, which are really the heart and soul of this method. The first step is in the estimation of single trial WPLV. We use the samples within all the trials, and we average the values over it, and we get a single trial PLV, right? After that, we have to associate these brain graphs to different movement classes. And how do we do that? Well, after trying various different kinds of methods, I realized that the most effective yet simple way of doing it is to basically look at those edges which show maximum contrast between the class labels that are involved. So for example, if you have 2 class labels and you denote them by +1 and -1, right? You effectively want to retain those edges which show maximum weight for one class and minimum weight for the other class, and in the reverse trend. So if we can identify these kind of edges from the overall brain graphs, then we can use them as features for single trial classification, right? This is different from the usual way of handling or analyzing brain graphs, because normally when we look at connectivity, we do statistical analysis and we just retain those links which are significant. The problem with that is a link can be significant for both the classes involved. So that does not really help us to classify the two classes, right? So instead, we want to really maximize the contrast between these 2 classes. So with that in mind, let's look at how this model, based on network interaction, works. So WCSP is the algorithm that I had alluded to earlier, and it was seen that it performed decently with 71.25%. The algorithm, which is using WPLV, is able to achieve about 77%. Well, more than the marginal increase in performance, this really goes to validate the fact that there actually is discriminative information in brain connectivity-based features for single trial classification, right? And in fact, this goes to validate our initial hypothesis that a model which is built on using information from different regions actually means that different brain areas probably are interacting in different ways, so that something like a fairly complex task wherein you have single hand movements in different directions is actually carried out. Right. So it is at par with the well-established algorithm based on CSP. But more importantly, let's look at what does this information really look like? Like what does this really mean in terms of the neurophysiological sense? So here we have 2 time frequency maps. And this is basically showing the interaction between 2 pairs of channels. In the left-hand side, which is associated to north direction, movement in the north direction, the channel pair which is used is C2CPZ. And we were able to identify this by basically isolating those features which were most commonly picked when we ran cross-validation across all the different subjects. Okay, so on the left-hand side, it is C2CPZ. On the right-hand side, it is FC1 and C2. So what you can immediately see over here is C2 is common in both. But the interaction that is very dominant is with CPZ on the left-hand side, but with FC1 on the right-hand side. All right. Now, on the x-axis is basically time, with t equal to 0 denoting the time for movement onset. So the subject already knew which direction he has to perform his movement in. So we can think of this 1 second prior to movement as movement planning, and that after it as movement execution. Okay. On the y-axis, you have wave levels, and as you already know, wave levels basically means it has different frequency bands. So moving from 1 to 6, you are basically moving from 0.01 to in my case 12 hertz, right? And so what you immediately see over here is that there are different time frequency pockets of interaction, of dominant interaction, right? So this probably is the reason why we are able to see different or discriminative information from such features. Okay, but let us now take a step further and try and understand what could this further mean, right? In terms of this whole temporal scale of going from movement planning to movement execution. Right. So this is an analysis of the entire temporal evolution of brain networks in terms of looking at the number of significantly phase-locked channels. All right. So when we do this over all the cross-validation iterations, what we find is that over all the subjects, there emerges a very common trend, which is common also for the 4 directions, in that this network starts off as something which comprises only a few channel pairs in the beginning, movement planning. It peaks around the time there is movement onset, and then again declines and goes back to, again, a low-lying network as execution finishes. So what does this mean? This probably means that such a network could, in fact, have a role to play in movement initiation rather than movement planning and execution. Right, but this, of course, is to be seen, is to be verified using neuroimaging studies, for example. So what we have seen so far is that there's definitely evidence of discriminative information in such features, and using single file classification, we can actually validate our hypothesis, because this is basically means that our initial hypothesis and an initial model is basically working quite well. And what we have seen is that there are different time frequency windows which show dominant interaction, and overall there is a buildup of activity, peaks around the time there is a movement initiation, and again declines, right? And we were able to model this without any assumption on the type of motor activity involved. There is absolutely no information given to the classifier about the fact that they are actually performing movements in 4 directions. So that actually means that such a kind of network, such a kind of model can actually be given to study different types of motor activity. Right, and this is what shows the power of data-driven modeling. Right. Now, so far we were limited to the EG sensor space, but then we know that in the EG sensor space, the problem is that you have signals mixed from a lot of cortical sources. So you perform source localization. There are a lot of standard techniques in order to do that. And then the problem is that we've got to find out some way in which we find the important nodes, because when we move to the cortical source space, there are so many more nodes as compared to the sensor space. Right? So without increasing the computational overhead, how can we identify the important nodes, and we can do it, something like a preliminary study before we actually carry out a very accurate source localization method. So in fact, there are standard techniques which actually exist in literature. So for example, you could use something like ICA, independent component analysis of the entire EEG data, which could then point to different independent components with the assumption that different independent components are actually resembling different spatially independent groups of neural sources. This is a very strong assumption, but then this is something that we can visualize, and then this is only to develop an intuition of which areas could be involved. In fact, when we use this approach for all the different directions from all different subjects and cluster them with the help of k-means clustering, what we find is that these clusters are located across the brain, not just in the motor cortex, right? So this possibly means that there is involvement of motor and non-motor areas, such as the cognitive areas and the visual areas, which play a role in such kind of motor activity. We can even use autoregressive methods to model the interaction between these different areas, and that leads to another different type of observation, actually, in that the strongest information flow was seen during the preparation stage. Earlier we saw that the extent of the network was highest at the movement initiation. But if we talk about the strength of the network itself, we see that it peaks actually around the time there is preparation. So what does this actually mean for a more cognitive basis? Again, that is to be studied with the help of more neuroimaging studies. So lastly, what we are basically able to conclude is that this is the visuomotor task, right? We cannot isolate the fact that there is visual and cognitive areas processing involved along with the motor activity. So with the help of data-driven approach, we are able to find that there's information flow happening between the visual and premotor areas. There are motor and non-motor areas involved. And in fact, this is the motivation for my ongoing work, where I use discriminative information from whole brain networks in the cortical space to identify finger movements and more complex fine movements. So to wrap up, I would like to say that data-driven techniques can, in fact, help us to classify different types of activities, and can also help us to learn about different types of neurophysiological phenomena. It helps to minimize prior assumptions on which areas could be involved, and in fact, that plays a direct role in network discovery. Now, network discovery is actually a very important part of autism. And that is something that I wish I could present over here, but my results are currently being validated, so I'm not able to. But I will leave you with this last point, in that autism is actually known to be an empathy disorder. The ability to empathize is attributed to the to integration of information from a lot of different brain areas. You have multi-dimensional information coming from different areas, and if there is some problem in the ability of the brain to integrate this would probably manifest in behavioral deficits that are seen in autism. So in fact, I'm able to use my methods to link brain with behavior. And that's all. Thank you.
Thank you, Tushar. Right on time. We have 5-minute questions.
Hey Tushar, great talk.
Thanks.
I just wanted to ask you a question about the movement protocols. Was that tightly regulated for the subjects in the study, just to make sure that the variation in the brain activations is not dependent on how the person is holding the lever, or like if it's a right-handed versus left-handed person moving the lever or not? So could you just comment on that?
Sure. So firstly, yes, the protocols are very well defined, and there is in fact always a supervisor who checks for all these abnormalities if they are present, and there is a check on the data quality and about how the person is holding it, and all those things are involved. The second thing is that these models are actually subject specific. So in that case, if a person, if they are supposed hypothetically, if there is some artifact which manifests in the way he is holding it, that would be common across all the different directions, right? So when we are taking discriminative and we are identifying the most discriminative information, right, these artifacts would most probably not be picked, right? But then that's a very hypothetical basis. Mostly we don't let it come to that stage. We control for that.
Thank you for the nice talk, and it fits very well with the conference. There has been quite some work also on cortical recordings, more invasive and population coding, Georgopoulos, other people. Could that guide some more, like knowing a bit the neuroanatomy and the neurophysiology of the cortex? Could that help to guide a bit more what happens at the EEG level, or is it better to ignore it? Or is there a way of mixing the two, some kind of hybrid, not completely data-driven, also a bit driven by neurophysiology?
Right. Thank you very much for the question. In fact, when we're actually looking at interpreting EEG data, right, Tiffany and I were just discussing that there is a lot of problem in terms of the noise levels of EEG that actually prevents us from interpreting too much. In fact, if we do that, then we really are inviting a lot of skepticism when we do that. So one of my philosophies when I'm analyzing this is to back up all of my observations with known network neuroscience and anatomical neuroscience. So while I have not done a one-to-one correlation study with invasive recordings, for example, the observations coming from such studies definitely help to complement what I have observed. And it is only when we are able to validate or have a strong conviction about a certain observation, when we contrast it with such studies, do we actually claim anything.
One more question, short one.
So very short question. How do you deal with the muscular artifacts recorded at the EEG level?
Right. So we do it at multiple stages. Firstly, our pre-processing is very, very detailed. And when we're trying to identify different muscular artifacts, we are looking at not just the data itself, we're also looking at the spatial maps, so we're looking at a lot of different parameters. So in the first case itself, we're trying to remove as many. So for example, if there is evidence of any muscular artifacts, trials are removed. So first of all, we try and minimize it. As far as possible. And in the other case is that, like I was answering Soptik's question earlier, in that if there is a certain muscular artifact which manifests across all different classes, which is because of a particular subject, then that will probably not be picked up, because we're doing this contrast analysis between them. So if it is something which is common in all the classes, then we just ignore it.
Let's thank Tushar one more time.
Thank you.
if I may, can I just ask you to switch your mic with Alessio? So.